गुरुर्ब्रह्मा गुरुर्विष्णु गुरुदेवो महेश्वरः गुरु साक्षात् परब्रह्मा तस्मै श्री गुरवे नमः.
Hey physics fans, and welcome back. Today we are jumping right into chapter 9, all about light. We're going to focus on the first two sections, which means we're exploring the basics of reflection and then unlocking the super interesting and kind of weird properties of spherical mirrors. We'll even solve a mystery you can find in your kitchen right now.
Seriously, go grab a spoon. Look into the part that you'd eat soup with. See that? Your reflection is completely upside down. Kind of freaky, right? Now just flip it over to the back, and boom, you're right side up again. It's the same spoon, same light, same you. So what is going on?
Well, that spoon in your hand is basically a mini physics lab. The inside curve that flips you on your head, that's one kind of mirror. And the back curve that puts you right side up, that's a totally different kind. To really crack this mystery, we gotta go back to basics and understand the fundamental rules of light itself. So, let's start at the very beginning. What's the core principle that makes anything visible at all? I mean, how does the world out there even get into our eyes? It really all boils down to one simple word: reflection. If things didn't reflect light, we wouldn't see anything, period. Light from a source, like the sun or a lamp, hits an object. It bounces off, and when that bounced light hits our eyes, our brain goes, aha, there's something there. It's so simple, but it's also kind of profound when you stop to think about it. And here's the thing about this light. It travels in a super predictable way, in perfectly straight lines. You want proof? Just look at the sharp edge of a shadow cast by any solid object. That clean line is there because light can't just bend around corners. And that straight path is what we physicists call a ray. Now, this predictable straight line behavior isn't just happening by chance. It follows two beautifully simple, unbreakable laws. And the best part? These laws work for every reflecting surface you can imagine, from a flat mirror to the curve of a spoon. Okay, this is just so elegant. The first law basically says that the angle light comes in at is the exact same angle it bounces off at. Think of it like a perfect bank shot in a game of pool. Angle in equals angle out. Simple. The second law just says the whole event, the incoming ray, the outgoing ray, and that imaginary perpendicular line we call the normal, it all happens on one flat surface. It's not some crazy 3D explosion. That's it. Those two rules explain everything else we're about to see. All right, so we've got the rules for flat stuff down, but our spoon is definitely not flat. So what happens when we take these unbreakable laws and apply them to a surface that has a curve? Well, we get something called a spherical mirror. The best way to think about it is to imagine a giant, perfectly mirrored Christmas ornament. Now, what if you just sliced a piece of it off? That curved slice you're holding, that's a spherical mirror. And that brings us right back to our spoon. Now, these mirrors come in two main flavors. First, you have the concave mirror. Its surface curves inwards, kind of like a cave. This is the inside of your spoon, the part that's making you look upside down. Then you have the convex mirror, which bulges outwards. And yep, you guessed it, that's the back of your spoon, the part that shows you a tiny upright version of the world. Okay, to really predict what these mirrors are going to do with light, we need a sort of map of their geometry. Think of the pole, P, as the "you are here" sticker. It's the dead center of the mirror's surface. The center of curvature, C, that's the original center point of the giant sphere we sliced our mirror from. And the straight line connecting them? That's our main highway, the principal axis. These are the landmarks we use to calculate everything. Okay, so we've got the rules and we've got the map. Now for the fun part.
Let's see the incredible things these mirrors can actually do with light. This is where we unlock their superpowers.
So a concave mirror, the inside of our spoon, it has this one amazing trick. It's a collector. It gathers up all these parallel rays of incoming light, and using those laws of reflection, it bounces every single one of them so they all cross over at one tiny precise point. We call that point the principal focus. And that focusing effect, by the way, is exactly why your reflection gets flipped upside down.
And this focusing power isn't just a neat theory, it's real. You can literally take a concave mirror outside on a sunny day, and it will gather all that sunlight and concentrate it into one little intensely bright spot. A spot so powerful it can focus enough solar energy to set a piece of paper on fire. That's the power of convergence.
And what's so cool is that this relationship is perfectly predictable. The focus point isn't in some random spot. It's located exactly halfway between the mirror's surface and its center of curvature. This little formula, R equals 2F, is the blueprint. It's what lets engineers building massive telescopes know exactly where to put their sensors. And it's what lets you build a solar oven in your backyard. All right, now let's flip the spoon over. If the concave side is a collector that focuses light to a point, the convex side is a broadcaster. It takes all those incoming parallel rays and scatters them, spreading them out and making them look like they're coming from a focal point behind the mirror. And this scattering superpower is, no joke, a lifesaver. It's exactly why the passenger side mirror on your car is convex, because it spreads the light out and shrinks everything down. It gives you this huge panoramic wide-angle view. You see way more of the road and the cars beside you in a single glance. It's trading a little bit of size for a massive field of view and a whole lot of safety.
And that brings us right back to where we started. The upside-down reflection in the bowl of a spoon, it's using the exact same focusing power that can start a fire with sunlight. The right side up wide-angle view on the back, that's using the same scattering principle that keeps you safe on the road. All of this from one simple object, all governed by two simple laws of reflection. So we've seen how the rules of reflection literally dictate how we see our world, and how a simple curve can become an incredible tool to either focus energy or expand our vision. The mystery of the spoon? Solved. But it does leave you with one last question to chew on. If these simple, elegant rules of geometry are shaping something as basic as light, what other invisible forces all around us are being quietly commanded by the simple shapes we see every day?